Chapter 3 introduces a lot of new definitions and vocabulary for us. Before you watch the examples in this video, make sure you do the pre-video notes, which provides a list of all the definitions, so start to familiarize yourselves with those. There are a couple of theorems that we're going to use along the way that are stated in the pre-video notes. If I prove them, it'll be in a different video, not in this one. So I thought that a good way to start to make sense of the definitions is to do a few examples that hopefully illustrate most of the kinds of things that'll happen. And then you'll have a few examples of your own to try for homework. All right, so the first example, these are all provided in the pre-video notes. But the first example is the reciprocals of the natural numbers with alternating signs. So this minus 1 to the n, right, if you start off with n equals 1, you get a negative, n equals 2 is a positive, and then it just flips back and forth. And then the denominators are increasing. So my first point is minus 1, and my second point is a half. And then I get minus a third, somewhere right here, and then a fourth, and then minus a fifth, and then a sixth. And so you can see that we're getting closer and closer to 0, but bouncing between the two sides. All right, so the first question in the example is whether or not this set is open. Now, in order to be an open set, I have to be able to take any point in the set and fit some epsilon neighborhood around that point that's totally in the set. So if I started with minus 1, for example, I think right away we have our counterexample, because no matter how small my epsilon neighborhood is around the point 1, that epsilon neighborhood is not going to be contained in the set, because the set is just a bunch of singletons, right? The union of a bunch of singletons. So because the epsilon neighborhood around the point minus 1 is not contained in the set fails to be open. Actually, we could have used any point, right? There are no points in the set that have epsilon neighborhoods that lie entirely inside the set. Right? If I took a half, tried to put an epsilon neighborhood around it that stayed in the set, well, I've drawn one there that fails. Next up is to find the limit points of my set. Now, a crucial thing about limit points is they don't have to be members of the set, and that takes some getting used to. So a limit point is one where no matter what epsilon neighborhood we choose, the deleted epsilon neighborhood around the point has to intersect the set. So for example, if I took minus a third, then that would be a neighborhood, right, not including minus a third, but that neighborhood would intersect the set. But if I drew a smaller one, the smaller epsilon neighborhood would not intersect the set. So minus a third fails to be a limit point. And in fact, all of these points fail to be limit points. Anything that's in the set is its own distinct point. So you can find an epsilon neighborhood small enough that separates it from the rest of the set. The one point that's different is 0. So if we think about 0, and I take a deleted neighborhood around 0, then no matter how small I take that neighborhood, points from the set are going to drop into that interval. So if I took epsilon to be 1 over 1,000, then I just have to go out until n is bigger than 1,000, and then I'll be inside that epsilon deleted neighborhood around 0. So we have found a limit point, and in fact it's the only one. So the limit points here is just the number 0. All right, now next up we have isolated points, and the isolated points, remember, are any points in the set that aren't limit points. And so we've already kind of shown that everything in the set is an isolated point. We only have one limit point, that one's not in the set, but everything that's a member of the set is an isolated point. So this is all points in the set. All right, next up is to figure out if the set is closed. Closed means the set contains all of its limit points. We only have one limit point, and the set does not contain it. So this set is not closed. So it doesn't contain 0. So here's an example of a set that's neither open nor closed, which is something else that takes a little bit of getting used to, because right, if you're talking about a door, the door is either open or closed. But for sets, it's a little bit more subtle than that. A set can be neither open nor closed, and it can be both open and closed. All right, what about bounded? Bounded just means we can fit the entire set inside some large closed interval. So there's got to be some capital M where we can fit everything inside the set in this large interval. The largest we can get in the negative direction is -1, and the positive direction is 1/2. So yes, this is a bounded set. And if you want a specific M, M equals 1 would do the trick, but so would 1 1/2 and 2 and so on. Just make sure your M is not smaller than 1, because this -1 here would give you a problem. All right, last question for this example is the set compact. Now, compactness is defined in terms of the convergence of a subsequence. Right, a set is compact. That means that every sequence in the set has a subsequence that converges to something that's also in the set. Thankfully, we have a theorem that simplifies figuring out compactness for us, and that's the theorem that says a set is compact if and only if it is both closed and bounded. So really this last column in the examples, that's just a matter of looking at the previous two, right? So if it's both closed and bounded, it's compact, otherwise it isn't. This first example wasn't closed, so it can't be compact. So no, it's not closed. Okay, our example is the interval from 0 to 2, not including the endpoints. So that's just going to look like this. First question, is it open? Well, we have to take any element in the set, so maybe this point, and then see if we can fit an epsilon neighborhood around that that's entirely in the set. And the answer here is yes, there's one. What if I took a point here? Well, there's an epsilon neighborhood that's still entirely in the set. And what about here? Well, I'm getting close to the end, but yes, as long as I'm not at the end, just shrink your interval enough that you can land it in the set completely. And the only possible problems are if you say, well, what about if I take 0 or 2? But 0 and 2 are not in the set, so it's okay if those didn't work out for you. So anything that's strictly between 0 and 2 means I'm a little off of the left endpoint, or at least a little off of the right endpoint, and as soon as that happens, I can fit that interval inside. Right? So yes, this set is open. All right, now what about the limit points of the set? Well, the first thing to note is that anything that's in this set is a limit point. So if I took anything inside the interval, then every epsilon neighborhood, every deleted epsilon neighborhood around the point will intersect with the set itself. If I took something out here, say -1, that's not a limit point because I can fit a deleted neighborhood around -1 that entirely misses the set. The ones that are a little bit ambiguous until we think about it is 0 and 2. Now, if I start with the point 0 and I try to put a deleted epsilon neighborhood around 0, on the left it looks like I might miss the set, but notice that anything on the right actually intersects with the set. So it doesn't matter how small I take that interval, the right-hand side of the interval is going to intersect with 0, 2. And then similarly for 2, right, I can put an epsilon neighborhood around 2. It's not entirely in the set, but that's okay. What matters is that it has to intersect the set somewhere other than 2. And that's the case for any epsilon neighborhood around 2. All right, so our set of limit points in this case is the original set together with 0 and 2. So that looks like the closed interval 0, 2. What about isolated points? Well, we actually can't have isolated points because we already said that any point in the set is a limit point. And the isolated points are the ones that aren't limit points. So we have no isolated points. Is the set closed? No. We found 2 limit points, 0 and 2, that are not in the original set. So the set doesn't contain all of its limit points. It contains a lot of them, but not all of them. So this set is not closed because it doesn't contain zero or 2. What about bounded? So I would say yes, we have a bounded interval, right? Any large enough capital M will include every element in the set. So this will be yes. And M equals 10 would work, right? The definition doesn't require the best bound. The best bound would be M equals 2, but anything larger than 2 is okay. And then finally, is the set compact? Well, we use the theorem again. It's compact if and only if it's both closed and bounded. It's bounded but not closed. So this is a no, not compact. All right, our final example for this video is the half-infinite interval that goes from -1 included and then everything to the right. All right, so first let's think about whether or not the set is open. Right? So open means I can pick anything in the set, and I have to be able to put an epsilon neighborhood around it that stays entirely in the set. So that's true for any point to the right of -1 for sure. But at -1, I think I've got trouble, right? Because no matter how small an epsilon neighborhood I try to put around -1, it extends to the left out of the set, so it can't lie entirely in the set. So this set is not open. So the idea here is we can't fit an epsilon neighborhood around -1 in the set. Right? Again, every epsilon neighborhood around that point extends to the left past the point, and so it fails to be in the set. All right, now what about limit points? Well, it's similar to the second example. Any of these points in the set to the right of -1, they have to be limit points because any interval around the point necessarily includes points in the set. Right, so that's going to be fine for all of those. Right, 0, for example, take any epsilon neighborhood you want. As soon as you extend past 0, you're including non-zero points in the set. So any deleted neighborhood around 0 intersects the set. All right, what about anything to the left of -1, say -2? That's going to fail to be a limit point because we just take a neighborhood small enough that the deleted neighborhood entirely misses the original set. So the interesting one is really -1, but here I think we can see we do have a limit point because while I miss the set to the left, any epsilon neighborhood to the right has to include points besides -1 in the set. So any deleted neighborhood around -1, because it extends to the right, has to intersect the original set. That makes -1 a limit point. And so our set of limit points looks like the original. Right? Everything in the set turned out to be a limit point this time. All right, what about isolated points? Well, similar to the last example, there are everything that's in the set is a limit point, so there are no isolated points. Is the set closed? Yes, this is actually our first example of a closed set. Right? The limit points turned out to be the same as the set itself, so the set contains all its limit points, and that makes it closed. So this contains, you say the set contains. All right, is the set bounded? Well, this is one example out of the 3 that is not bounded, right? No matter what I take capital M to be, the fact that I go off to plus infinity here means if I take 2m, right, I'm past the bound but in the set. This is an unbounded set. I'll just say unbounded to the right. And finally, is it compact? Well, it looks like we did not have any examples of compact sets because the last example, while closed, isn't bounded, and you have to be both to be compact. So this is no, not bounded. Okay, so there are 3 examples of how to think about openness, limit points, isolated points, being closed, bounded, and compact. Hopefully this will start to make sense as you work through some examples, both in this video and the ones that you'll have to try on your own. So I will see you in class.